In this video, we're going to talk about trig identities and complementary angles. Alright, just as a quick refresher, when we talk about basic trig, we're talking about right triangle trigonometry. So a review of the 6 basic trig ratios are our sine, cosine, tangent, and the inverse of those 3, cosecant, secant, and cotangent, using this right triangle here, given some angle theta and the relationships between adjacent, opposite, and hypotenuse sides. Another cute little trick to remembering this is SOHCAHTOA, and you can remember it as just this guy here, or these triangles, depending on how you like to remember things. So let's take a look at an example that uses all 6 trig ratios. So let's say I'm given sine of A, which is an angle that is acute, and that ratio is going to be equal to 1/3. Let's find the exact value of the remaining 5 trig functions. So the first thing that I'm going to want to recall is SOHCAHTOA. You can remember that in any way that you would like to. So a cute little trick that I use is if I know sine of A, I'm going to pretend that I'm standing at angle A, and knowing what I know about sine, and I have my first letter here, which is O, so opposite of this angle is going to be side little a, and that's the value of 1 because it's 1/3, right? So the hypotenuse is always straight across from the right angle. So that's going to be equivalent to 3. So that's my 1/3. Now I need to figure out what this remaining side is going to be. So I'm going to use the Pythagorean theorem. So I know that 3 squared equals 1 squared plus this question mark squared. And if I work that out, I'm going to get that that side is actually equivalent to 2 radical 2. So now let's find my cosine, tangent, cosecant, secant, and cotangent. So the first thing is I'm going to use my cosine of A. Please keep in mind that when you define cosine, tangent, etc., that you have to have it of some angle. So whether that's theta, A, B, or C, or some degree measure, you always have to take that trig ratio, sine, cosine, tangent, etc., of an angle. Without that angle, it's not correct. So if the cosine relationship is adjacent, so adjacent to me here is actually my 2 radical 2, all over the hypotenuse, which is 3. That's my cosine of A ratio. So using the same logic, let's take tan of A. So I could do one of two things. I could take my ratio of sine, which is 1/3, and put it over my ratio of cosine, because tangent is over cosine. And luckily for me, these are going to cancel to give me 1/2 radical 2, or if I simplify that down, it gives me radical 2 over 4. So if I wanted to find the inverse of these functions, once I have sine, cosine, and tangent, I literally just flip them around. So the inverse of sine is cosecant. And another little trick that I like to use is that between sine and cosine, to keep cosecant and secant straight, I know that S goes to C, right? So the S of sine will have a relationship with this cosecant here. So cosecant of A is going to be the inverse of 3/1, or 3. And the secant, right, so C goes to S. Secant of A is going to be the reciprocal of this, so that's going to be 3/2 radical 2, which if I actually work that out algebraically, that's going to be 3 radical 2 over 4. And last but not least, my cotangent is going to be the reciprocal of 4 over radical 2, or just 2 radical 2. So those are my 6 trig ratios. 1/3 is sine, 2 rad 2 over 3 is cosine, rad 2 over 4 is tangent, 3 is my cosecant, 3 rad 2 over 4 is my secant, and 2 rad 2 is my cotan. Something else I can do with right triangles and the Pythagorean theorem is develop something called a Pythagorean identity, or a trig identity. There are actually 3 of them, but they all stem from one equation, which actually comes from right triangle trigonometry and the Pythagorean theorem. So if I start off with my right triangle here, which is triangle ABC, where the right angle is at angle C, for example, and I have my Pythagorean theorem, which is a squared plus b squared equals c squared, and I'm going to define some angle at A, which is theta. So the trig part's going to come in here in just a second. The first thing I'm actually going to do to start off this proof is to divide everything by c squared. So go with me. So if I divide a squared by c squared, that's like saying a over c squared plus b over c squared equals, you guessed it, c over c squared. My 2's are looking hideous. I'm so sorry. So if I'm at a over c here, right, this little a and this little c, that relationship is like, that's opposite, right, over hypotenuse. And knowing SOHCAHTOA, I know that the relationship between O and H is in sine. So that's like saying O over H squared. Now if I do the same thing with my B over C, B from theta is my adjacent, and C is still my hypotenuse. So that's like saying adjacent over hypotenuse squared is equal to C over C, that's 1 squared. So if I replace the OH with sine, now I'm going to use my theta because it has to be of something, plus A over H, that's cosine theta equals 1. I developed this thing, this equation, which states that if I have some value of theta, and I take the sine of that angle, so let's say it's 30, right? And then I square that value, and I add it to the cosine of that same angle, and I square that, that will always give me 1. So that is what we call our Pythagorean identity. So like I said earlier, there are 3 of these, and this sine squared theta plus cosine squared theta equals 1 is the most basic one, or where the other 2 come from. Also, I'd like to point out that when I squared it in the last slide, I squared this whole thing, which we represent without the parentheses, as the square going as an exponent next to the sine or the cosine. That's just how we write it. So if I was to actually square just the theta without the parentheses, that means something different. That just squares the angle itself. But we're talking about the entire trig function here. We'll talk about that at a later time, but that's just an important difference to know. So the way that we come about solving for the other 2 trig identities is that we take the entire equation and we divide it either by sine squared theta or cosine squared theta. So that will pump out 2 different equations. So let me show you how that works here. So if I divide this whole thing by sine squared theta, for example, I'm going to get sine squared theta over sine squared theta, that's 1, plus, now cosine over sine is the inverse of tan, so that's cotan squared theta, because we still have the square over square, and that's going to give me 1 over sine squared, so that's the inverse of sine, right, and I know s goes to c, so that's my cosecant squared theta. So that's my second Pythagorean identity. You may also see it as cotangent squared theta plus 1 equals cosecant squared theta. Same thing. And in order to find the other one, instead of dividing by sine squared theta, let's divide by cosine squared theta. Same thing, same process at least. Sine over cosine is tangent squared theta, and cosine over cosine is 1. And the inverse of cosine, or 1 over cosine squared, is secant, because remember, c goes to s, secant squared theta. So that is our third Pythagorean identity. So you may be thinking, well, that's really nice. What do I do with it? Well, there's a lot of things that you can do with it, but let's start off really simple here. So let's take a look at our first example. If I'm given sine squared of 20 degrees plus cosine squared of 20 degrees, I can recall a fact that I know, that if I replace this 20 with some theta measurement, sine squared theta plus cosine squared theta, as long as it's the same angle measurement, that's going to give me 1 because of that Pythagorean identity. That's going to be something that you're going to want to commit to memory. So another thing I can do is I can create something out of this. So whether it's an identity or a reciprocal or an inverse, whatever it is that you want to work with, I can take this here and I can compare them all because it's like working with the same angle or theta. So that's like saying tan of theta minus, now remember, sine over cosine is tan, and 50 is my theta. So that's like saying the same thing minus itself gives me 0. Something else to be reminded of is the relationship between two angles that we call complementary angles. So those are angles that add up to 90. And a nice little trick to remember that is there's a difference between complementary and supplementary angles. So before we talk about supplementary angles, which will be for another video, is that you're going to have a C and an S. I'll show you both right now. So the way to remember that complementary makes 90 is to draw a dotted line straight down from the C. And that kind of makes a 9. And if you draw a dotted line through the S, that makes kind of like a 180. Cute little trick to remember that. So complementary angles, both of these guys are going to add up to your 90 degrees. So the reason that I bring up complementary angles is that there's this thing called the complementary angle theorem. So it looks more complicated than it is. So what it says that if you take the sine of a certain angle, let's say it's 60, it's actually going to equal the cosine of the difference of that angle in 90. So for example, if you had sine of 60 degrees, that's going to be equal to the cosine of 30 degrees, because 60 plus 30 make 90. So the relationships to know are between sine and cosine, tan and cotan, and secant and cosecant. So they're also rewritten down here, because if you work with 90 degrees, that's the same thing as saying pi over 2. So let's work through two examples. So let's say I have this first one here, secant of 28 degrees minus cosecant of 62 degrees. So I know that secant and cosecant are what we call co-functions. They are co-functions of one another that make up complementary angles. So 28 and 62 make 90. So secant of 28 is like saying cosecant of 90 minus 28. And 90 minus 28 is 62. So the cosecant of 62 minus the cosecant of 62, well, that's 0. So let's take a look at another one. Now, I have sine 35 degrees over cosine 55 degrees. So if that was actually the same degree measure, we could just call that tan of whatever degree measure and call it a day. But I have to actually recall some other kind of relationship. So sine and cosine are co-functions of one another, and they make up the 35 and the 55, that makes 90. So co-functions, complementary angles, 90 degrees. Let's rewrite this. So I'm going to rewrite sine of 35 as cosine of 90 minus 35, and that's going to be the same as cosine of 55, and cosine of 55 over the cosine of 55 is, you guessed it, 1. And that's going to do it for this video. Thanks for watching.